All right, so this is a experiment for the continuous floating origin. I had an idea that fixes some of the issues that some people in this forum post were talking about. I don't know if this is a new idea or not, but I came up with this system that I think solves potentially a number of issues in certain circumstances. I don't think it's going to fix anything like physics inaccuracies at long distances, but this might solve some people's problems. So what my idea is, and it might not be original at all, I don't know. But this one is going to be continuous floating origin. So this is representation on the left side. You can see that the character or the player here is going to be centered. Let's see, I'll just move the game window over here so you can see that. We have basically two identical levels, but on the one level, this character has a continuous floating origin, so he's 0, 0, 0, and the level's moving around him. On the right side, we have just a standard level where the character is moving within the static world. So my idea is basically to use the colliders and the static geometry from a typical game world, and you kind of just use the continuous floating origin as a game layer or as a layer to display the outcome of that. So, for example, all of the colliders and the control is done on the right side on the normal world, and it's simply being displayed to a character whose origin is 0, 0, 0 on the other world. So basically, you instantiate your world 2 times, and then you take your all of your colliders and static marks, and static geometry in the world with the continuous floating origin, because according to the forum post, there was problems with colliders being moved, or potentially problems with massive amounts of colliders being moved. So now there are no colliders on this display layer, and all the colliders become static on the other layer. So I think that might potentially solve some issues for some people. If you get 5 kilometers out or whatever, you still have the issue with things are inaccurate by a centimeter or an inch or whatever. But you have a layer of abstraction to then take care of those issues visually. Like you can't really get super accurate physics, but you can make it appear as though you do, because you could just say, if give me a position, and unless the position moves greater than the potential error of the float value, don't update it. And that way, if you have an item or something like that, it's not shaking. It's still stuck in one position, even though the float error is there. So I think maybe using this hybrid approach or something could be suitable for some projects, and potentially allow some open world projects to be successful when they otherwise would not have been. So hopefully this was of interest to you, and I don't know if this is an original idea at all, but hopefully it can be applied for some solutions, and I'm going to attempt to apply this solution for my own game that I'm working on here, because I have it's a VR game, and VR seems extremely sensitive to those jitter issues, probably because the float error is probably calculated differently per each eye, so you're kind of getting a 3D compounding of that error, so it seems even more prevalent in VR than it is on desktop or a PC. So yeah, this is my potential solution to the issue. So hopefully it scales well and works well. But I guess I'll keep you guys updated and let you know how it works out on the actual world, which is 20 kilometers big. So yeah, cool. Have a good day.